This screencast, we're going to look at intermolecular forces, and we're going to focus on the three types of forces, the three main groups we're going to focus on. London dispersion force, we're going to investigate dipole-dipole and also ion-dipole forces, and then we're going to look at hydrogen bonding, which is also labeled as an intermolecular force. Alright, this graphic lists the three types of intermolecular forces, and also it is really important, I would make sure that I included this in my notes, this particular scheme of weak and general intermolecular forces up through strong intermolecular forces. You will want to recognize that the London forces are the weakest and hydrogen bonding is the strongest. And what you're going to be doing after you recognize the different types of intermolecular force in a molecule is you're going to compare two molecules and go, okay, well, this one would have a higher melting, boiling, etc. point, or this one would have a lower because it has hydrogen bonding or it has an absence of hydrogen bonding. So the order is London dispersion forces, dipole-dipole, ion-dipole, and hydrogen bonding. Alright, dipole-dipole. In a dipole molecule, remember, we have two ends, and this end would be slightly negative, and this end would be slightly positive. A dipole is the presence of oppositely charged ends. The electrons exist more around chlorine, as we learned when we did the dot diagram, and there's less electrons around hydrogen. So the hydrogen end has a positive charge and the chlorine end has a slightly negative charge. The molecules in HCl, when you pour them into a beaker, are going to arrange themselves so that they are a negative side chlorine will be next to another positive side hydrogen, so that they can not repel each other. Just like two magnets, if you have two north ends of magnets together, they're going to push each other apart and repel. But if you put a north and a south together, they will exist nearby peacefully. So hydrogen chloride, or HCl, will arrange itself so that it has the neighboring molecule facing the same way, so that you have this negative ended side here nearby the positive side of the next hydrogen. These molecules have to be really close together in order for this attraction to occur, and the strength of this attraction will depend on how polar they are, if they're similar in sizes, or if they are similar in mass. So if you have an uneven sized molecule, like one side of hydrogen is much bigger or smaller than the other side of the chlorine, it could be harder to form this dipole-dipole force because you have to get that hydrogen pretty close to feel the effect of the positive end. An ion dipole is very similar to a dipole-dipole. The difference is that you have introduced an ion in your polar solution. So you have your polar molecule, so like your HCl, and remember this end is partially negative and this end is partially positive. So if you introduce a negative ion or a positive ion into the solution of hydrochloric acid, the ion will attract itself to one end or the other of the existing polar molecule. Again, it's going to depend on the size of the molecule and the strength of the dipole, how attracted this ion would be. It does have to be close, but not as close as a regular dipole-dipole. Ion dipole is considered to be stronger than dipole-dipole forces, and both of them are stronger than London dispersion. Hydrogen bonds are a unique, very strong intermolecular force that only is seen with hydrogen and these three elements, so F, O, and N. Hydrogen must be one of the participating elements, and then either fluorine, oxygen, or nitrogen, the elements with the strongest electronegativities. What happens is that the hydrogen, being the positive end, is attracted to these very negative elements, and it causes a hydrogen bond or an attraction to occur between the molecule. And if you look at water, which is H2O, you have your hydrogens on the end, which remember are positive, and then you have these unpaired electrons. And these unpaired electrons will attract to the next water's hydrogen. So you have a hydrogen bond that occurs here. And it is not a real bond, it's a very strong attraction. And it is why water has so many unique properties that it does. For instance, it causes ice to float, you have a great surface tension, you have a very high specific heat, which allows animals, like pond animals, to exist in a lake because it takes a lot of energy for the temperature to change. All right, so the last force is London dispersion forces. A London dispersion force is kind of like a dipole-dipole, except that the molecules are not polar. These only occur with non-polar molecules. And what happens is they become temporarily polar. So they're referencing it as an induced polar molecule. What happens is as the electrons orbit around the two molecules, sometimes they're on the outside and sometimes they're on the inside. And what will happen is when they are both on the outside, you have an uneven shift. And so the one that I have shown here would have the slightly negative side on that on the right and the slightly positive side on the left. And so if they all line up just so, you would have an attraction here in the middle. Now, it's weak because you are dependent on these electrons orbiting around the molecule, and it only happens for a moment when the electrons are all in alignment. So it is brief and it is weak. And you will need to have these molecules be very close together, so they have to be similar in size, and it will not have as much of an attractive force as dipole-dipole or hydrogen bonding, so these are exceptionally weak. This is another image of London dispersion forces, and you can see the cloud of density for the electrons. And in the picture, they have indicated that the electrons for this brief moment are on the outer two edges on these hydrogen molecules, which hydrogen molecule is nonpolar. And if they bump into each other in just such a way, you have the negative and the positive here causing an attraction. It's brief, it has to be close, and it has to be arranged in just such a way that it can attract. Okay, so that is the three types of intermolecular forces. There is London dispersion, there is dipole-dipole and ion-dipole, and then there's hydrogen bonding. And depending on what type of intermolecular force you have, which type of IMF you have, will indicate what kind of properties the substance can take on. Stronger IMFs equal stronger, higher melting, boiling, and freezing points.